What we were introduced to in the previous part of this lecture is the definition of resistance, for which we use the symbol uppercase R, and uppercase R resistance is defined to be the potential applied across an object divided by the current that passes through that object. And a related definition that we're now introduced to is resistivity. And resistivity uses the Greek symbol rho, and so we see an overloading of the symbol rho here. We also use rho to describe volume charge density, and rho is frequently also used for mass density. And so we'll have to recognize by the context whether we're using rho for resistivity or rho for volume charge density. The difference between resistivity and resistance can be understood as the resistance of an object, which is uppercase R, depends on the size and the shape of the object and also on the material of which it's made. Resistivity, on the other hand, only depends on the material of which an object is made. So it takes the size and the shape of the object out of the picture. And resistivity, depending only on the material, is something that we can then quantify as a function of material. And that's what's shown in this table, which is from this chapter in the text. For example, the first entry is aluminum. If we consider aluminum, it has a certain resistivity rho associated with it, which is 2.8 times 10 to the negative 8, and the units of resistivity are the ohm meter. For different types of materials, when you're given a problem and you're asked for the resistivity of something and they give you the material, you would go to this table then to look up the resistivity. So if they give you, for example, that is copper that we're considering, then you would look up the resistivity in this table. A related definition is the conductivity of a material, and conductivity uses the Greek symbol sigma, and conductivity is defined to be 1 over the resistivity of a material. So the definition of conductivity is shown in this red box, and the conductivity then is calculated as the reciprocal of the resistivity. So if we take 1 over the resistivity in the first column for aluminum, 1 over 2.8 times 10 to the negative 8 will equal 3.5 times 10 to the 7. So these definitions then of resistivity and conductivity are redundant with each other, and just depending on the problem, they may have a preference asking you for conductivity or resistivity. The lower the resistivity, the lower the resistance. And similar to how we defined resistance, R is equal to delta V over I, we have a similar definition for resistivity, which is that rho is equal to E, where E is the electric field that's been applied to the material, divided by the amount of current density that flows through the material. So if we have a high amount of current density, then the resistivity is low and vice versa. And we could work out for the units from the units of electric field and current density that the SI unit of resistivity is the ohm meter. So if we have rho is equal to E over J, the units of the electric field are the volt per meter, and the units of the current density are amp per meter squared, and a volt per amp is an ohm, the unit of resistance, and one of the meters in the denominator of the denominator is going to cancel with that on top, and that's going to leave us with just a meter on top. So that's how we get to the units of resistivity. So the definition of resistivity For a given electric field passing through a material, if the current density that we measure is high, then the resistivity of that material is low. So to relate this new definition of resistivity back to the concept of resistance, we can start with our definition of resistivity. Rho is equal to E over J, and the electric field, if we have a uniform conductor of uniform cross-section, the electric field in that conductor is going to be equal to the potential difference applied across the conductor divided by the distance over which it's applied. So the electric field is equal to the rate of change of potential measured with respect to distance. So if, for example, what's shown in the illustration on the right, we apply a potential difference across the two ends of this conductor of delta V, and we divide that delta V divided by the distance, then that will tell us the strength of the electric field in the material. And this is just making use of the Mr. Ed relationship, which is change in potential is equal to E times D, and rearranging for E, we can write it this way, and in this case, the distance is L. Then current density by definition is equal to current per area, and then we see our definition of resistance emerge. Delta V over I is resistance, and then the A in the denominator of the denominator can be moved to the numerator. So finally we end up with resistivity is equal to resistance times cross-sectional area divided by length of the object. And this formula then can be rearranged to write that resistance is proportional to the resistivity of the material, and resistivity times the length of the object divided by its cross-sectional area can be used to calculate the overall resistance of the object. And this formula is only good for a uniform conductor, so uniform composition of uniform cross-sectional area. But for us, that's quite good. So we will only deal with conductors of uniform composition and cross-sectional area. So this formula will work well for us to relate resistivity to resistance. Okay, so we'll try an example with this new definition. So our new definition is resistivity is equal to the electric field through the material divided by the current density. And then also we've seen that resistance is equal to resistivity times the length of the component divided by its cross-sectional area. And in this example, it describes a 20 centimeter long hollow nichrome tube of inner diameter 2.8 millimeters. So I'll start with a sketch so we can visualize. The length of this nichrome tube is 20 centimeters. And the inner diameter I'll label as A, and that's 2.8 millimeters, or 2.8 times 10 to the negative 3 meters. And the outer diameter of the tube I'll label B, and that's 3 millimeters. And the tube is made out of nichrome. And that will be important so that we can access the table to determine the resistivity of nichrome. And the nichrome tube is connected to a 3-volt battery. So we apply a potential difference across it. And the question is, what is the current in the tube? So we're looking for I, and because the positive side of the battery is on the left, current will flow through the tube from left to right in my picture, back towards the negative terminal of the battery. So that's the conventional current flow. And we're looking for the value of I. So for nichrome, we can go back to the table that was just shown and look up what its resistivity is. And so in this table, I see nichrome. And the resistivity of nichrome is going to be from the table 1.5 times 10 to the negative 6 ohm meters. And so that's a much higher resistivity than, say, copper. And so this is about 2 orders of magnitude higher in terms of resistivity than copper. And so we know that nichrome is not going to be an especially good conductor. So we'll use that value for nichrome. Rho is equal to 1.5 times 10 to the minus 6 ohm meters. And then to solve this problem, we know that we have an equation that involves current and resistance, which is that resistance is equal to potential difference divided by current. So this would be a good equation for solving this problem if we knew what the resistance of the nichrome tube was. So this will be equation 1. And for the resistance, we can bring out our new equation. We can find the resistance of the nichrome tube by multiplying the resistivity of nichrome times the length of the tube divided by its cross-sectional area. So the material of which an object is made is just one part of its resistance. Also, what goes into determining its resistance is its dimensions. And so I am given the length of the nichrome directly. That's something that appears in our list of givens. And now I need to find the cross-sectional area through which the current flows. So the area that I'm looking for is this area. This is a hollow nichrome tube, so I can't count the area of the cavity within the nichrome tube. So to calculate the area, we would take the area of the outer circle, which is pi b squared, and subtract the area of the inner circle. And so this would be pi b squared minus a squared. And that would be this cross-sectional area of the nichrome tube. And so then I can plug equation A into equation 2. I'll call this equation 3. So we're now going to sub 3 into 2, and then 2 into equation 1 to work our way back to our calculation for current. So let's move to a new page. Okay, so if I do those substitutions, I had that A was equal to pi b squared minus a squared, and I'm going to substitute it into R is equal to rho L over A, which will give rho times L over pi b squared minus a squared. And then that equation I'm going to substitute into the equation for I, which said that I was equal to delta V over R. So I is equal to delta V over rho L, and the pi b squared minus a squared. So for delta V, I've got 3 volts. And then I'm multiplying it by pi. And B squared is 3 times 10 to the minus 3 meters squared minus 2.8 times 10 to the minus 3 meters squared divided by the resistivity of nichrome, which was 1.5 times 10 to the minus 6 ohm meters, and then times the length of the nichrome tube, which is 0.20 meters. And this calculates to, for the current, 9.1 amps. So with a voltage of 3 volts applied across the nichrome tube, we would measure a current flowing through the tube of 9.1 amps, which is a pretty decent size current. And that's an example of how we would make use of this new equation, which relates the resistivity of a material to the resistance of an object created from that material. And it's worth looking at this equation a bit more just to make sure that it seems okay, test it against our intuition. And what this relationship says, first of all, is that if the resistivity of the material goes up, then the resistance of an object made from that material will go up. And that makes sense. Some materials are going to have more free conduction electrons, and they're going to have a lower resistivity, so current will flow more readily through them, and therefore their resistance will also be lower. So resistivity and resistance go together in terms of if one goes up, the other goes up. But then let's look at the other two parameters, the L and the A, that appear in this equation. This equation says that the resistance will decrease as the cross-sectional area A increases. So A is in the denominator. If A goes up, then the resistance of the object is going to go down. And to get a feel for that, there's an animation that's shown on the right where we have a thin area, a thin wire of small cross-sectional area, and then a thicker wire of large A. And some positive ions are shown and then some conduction electrons. And if we activate the animation, we can see the flow of conduction electrons. And the conduction electrons are moving at the same individual rate, but there's simply more of them passing through the wire of the larger cross-sectional area. And more electrons flowing past a cross-sectional surface per unit time means that we would measure a larger current, and then we would say that the resistance decreases. So we get a lower resistance simply because we have more conduction electrons passing through a given cross-section for a thicker wire than we do a thinner wire. The other part of this relationship to look at is the relationship between resistance and the length of the component. This relationship says that if the length of the component increases, then the resistance of the component is going to increase as well. And this is a little bit harder to understand, I think, than the relationship between resistance and cross-sectional area. So we've got a short length and then a long length. And if we apply the same potential difference across these two components, the electric field depends on the potential difference applied across the element divided by the length of that element. And so that's just the E equals delta V over D formula that's applicable when we have a uniform electric field. The electric field is determined by the rate of change of potential over distance. So if we are applying the same potential difference across a longer length, that is going to have a smaller electric field. And so the second case with the long length will have a smaller electric field acting over the length of the material. And if we have a smaller electric field, it means we have a smaller force that's exerted on the conduction electrons. We'll see the drift velocity decrease in that material, and hence we'll see the current density and also current decrease. So the resistance is going to then increase. So we measure resistance as applied voltage over current, and if we measure a smaller current, then that implies a larger resistance. So the longer the length of the component, the larger the resistance of that component. And so we see the resistance of a component depends on three things: the resistivity of the material of which it's made, the length of the component, and the cross-sectional area of the component. And with that, I'm going to give you a lecture quiz question to try out this new equation, which is R is equal to rho times L over A. And one thing I want to point out about how to interpret these pictures, the blue line, the horizontal axis, represents the wire carrying the current. So current in each of these pictures is going from left to right. And then what you're given as dimensions are, the top dimension will be the length of the component, and the side dimension represents one side of the cross-sectional area, and each object has a square cross-section. So if it's 4 along this dimension, then it's 4 along this dimension as well. And this will represent the area, which in this example would be 4 squared. And so, for example, for the next object, its area is going to be 2 squared. And so you can use those dimensions, the given dimensions, to help you rank the resistance of the 3 components shown. And then that will end this part of the lecture. When we come back, we'll introduce Ohm's law.